thanks everyone for joining us today. And yeah, we're kind of going down that biology route. So it sort of ties in with that advert there that we saw. So we're going to be taking a look at Mother Nature versus Java, specifically taking a look at this security face-off. So Steve and I will be going head to head on this security battle, looking at sort of how we can take inspiration from nature, what tools we have available in Java, and how we can better integrate security into our development processes.
Yes, exactly. And this time I'm going to win.
So a little bit about us.
Yeah.
So my name is Grace Jansen, and I'm a developer advocate at IBM in the UK. I mostly work with sort of cloud native technologies, whether that be sort of looking at mostly around Java, so looking at things like the runtimes like OpenDivity, through to open source tools like Microprofile and Jakarta-EE, through to sort of methodologies and all the rest of it. But actually, before I did software engineering, I was a biology graduate. So I love to bring in nature analogies wherever I can into my presentations, which you'll see if you've been to any of my other talks. So hopefully I'll be bringing that in today. And I'm here with Steve.
Yes, so I'm Steve Poole. I'm not Grace Jensen. You can tell I have less hair. I am a developer advocate for Sonatype. But what that really means is that I am passionate about teaching Java developers and others about security and secure supply chains, because as we know in this modern world, there's a lot of bad guys out there, and we need to improve the things, how we deal with all this. And so this is a great talk because we're going to compare Gracie's experience as a biologist with my experiences with how the bad guys operate and how we as developers behave as well. Cool. So Grace, you'll do the next slide and I'll kick it off. Yes. So there we go. We want you to think differently, getting your head around about how security works and how you should think about every part of it. It can be difficult. So we just want to give you some examples from biology so that may make you think differently. And of course, the hope is that we're going to show that we are already better than Mother Nature. Yes, yeah, because Mother Nature's had a long time to develop these solutions, but because we're bright human beings and we invented Java, so no doubt I am totally convinced that when we look at this, we'll be seeing that actually we're already there. We have little to learn from Mother Nature. I'm hoping, yes. Thank you. So the way we're going to break this down is we're basically going to, it's just with the cage fight, we're going to look at things from these four things. We're looking at threats and challenges so that you understand what the bad guys do, and obviously from a natural point of view, what the threats and challenges are. We'll look at prevention. So what happens to prevent you getting attacked or getting ill or whatever. Then we'll look at detection, which is how well do you know that you've been hacked or you've been infected. And then finally, we'll look at what is in place in the systems to mitigate that. And mitigation isn't about an after the fact thing. It's like, what do we build into systems? What do we build into our bodies that mitigate any of these sorts of attacks? So thank you. Yeah. So the bad guys out there, and I think we can probably agree that it's not just what the bad guys do. I suspect that biology is just the same. People learn new ways of attacking us because they have new motivations. And I'm sure that we'll see that that's the same in biology as well. But there are bad guys out there, and they're getting very, very sophisticated in how they try and compromise our systems. Thank you. Yeah, so there are ways to look at this. So drive-by attacks, that's literally when it's an opportunity. It's like you left the window open in your system and they just drive by and discover that. So that's still happening. Next one, thanks. Yeah. And ransomware still happens. So ransomware is where they get into your systems and they compromise them. They encrypt your data and then charge you to get the data back. That still goes on. Okay, next. Yeah. But the big takeaway that you have to get from this in terms of all seriousness now is that the way that the bad guys behave, their motivation, what's in it for them is changing. And now we're looking much more about supply chains, how things get from A to B, whether it's money, goods, information, and the bad guys are trying to get into their infiltrate this infrastructure, get into the services so that, next slide, please. The objective is to manipulate these systems. So it may be something simple, like they corrupt addresses. It might be something a bit more sophisticated, where they switch addresses. Imagine what would happen if you had a supply chain that was delivering milk to your local supermarket and the addresses were switched. You know, imagine what would happen with Amazon if all of the packages being shipped ended up going to the wrong place. That would be tremendously disruptive. So you've got to understand, these are what's going on. These people are working hard to compromise our systems so that at some point in the future, they can use them to disrupt our economy and potentially even, you know, completely destroy it. And this isn't open to bag. This isn't just rogue nation states. You've got to understand that this is happening and this is going to happen because this is now the new way that cybercrime has evolved, and it's now become a national weapon. So every nation state is going to be looking into how they can do these things. Now, whatever they're trying to do, whether they are motivated from a economic point of view, whether they're motivated from a monetary point of view or from a government point of view, there are these basic things that they're going to try and do. And you can read them yourself, but I'll call them that. They're going to try and steal your data. Obviously, information you've got is useful to them. They're going to change your data. And so can they get in there and disrupt you or do things more nefariously? They're going to try and crash your systems, because obviously if I can bring it down, then you can't function. And we've all seen denial of service attacks and things like that. They will also try and use your compute power, because they can use it to get into other systems, or literally, as we know happens a lot, is they're going to use your compute power to do things like Bitcoin mining. And then finally, they want to compromise your systems to go from your system to somebody else's system, because you know other people, and if they can get through your system to somebody else, that can be easier than going direct, etc. Okay, so I've said all that. The bad guys are out there. They have various ways of how they're attacking us. They have various objectives. How does that work with biology, Grace?
So we have some similarities here, and I'll call them out as we go through. So the first thing I want to do is take a look at, okay, Steve's shown us some of the bad actors that we can come across in terms of software. What about biology? So when it comes to biology, there's a whole range of different bad actors that are trying to invade our bodies, trying to take over and utilize our bodies for various different nefarious purposes. It's kind of similar to what Steve was talking about. So some of them are things like viruses, which many of us will have heard of, especially given the global pandemic that's sort of occurring / just occurred. Things like, we can also have bacteria. It's the reason that we're supposed to, wash our hands, cook food, etc. Fungus, parasitic worms, and protozoa. So all of these different types of bad actors are essentially constantly trying to get in and infect us and use our bodies for different purposes. And that might be to use us as a host, for example. So they might just want a warm, comfy place to live, which our bodies tend to give them. They might want to use our bodies to replicate and grow. A lot of these bad actors are very simplistic organizations. They tend to be just a single cell big, and often they don't have the mechanisms they need themselves in order to replicate themselves and grow in terms of numbers. So they need our more complicated systems to be able to enable them to do that. They might want to, as Steve mentioned, go through us to infect others. Similar in software, similar in biology. That's how the common cold spreads. It deliberately wants you to sneeze everywhere, spread your germs, spread that bacteria, and infect the next person. And that's often why the common cold can spread so easily, and sort of one of the purposes of infecting us. Or they might just want to be parasitic in terms of taking over you or your body for its own benefit. That might be to put it in a position where it can get more food, where it might be protected from things trying to eat it. And actually, this is more common than you'd think. If you're squeamish, look away now, or if you're not, then feel free to take a look. If you thought zombies weren't real, you are so wrong. Zombies do exist, and here is an example of a zombie beetle. So for those of you who can't quite make it out because the resolution's not fantastic, but this is a beetle that is hollowed out. So this beetle is dead, very much so, but there is a parasite in its brain that is essentially controlling the nervous system like a puppet to move this beetle. So it's taken over the beetle, even though that host is dead. It's been able to take over its movements to be able to get it to move to a more beneficial location for it. So it's just a fascinating example of how bad actors in biology can go to this extreme of completely taking over the functions within not just body parts, but the entire body to manipulate the host to gain advantages depending on what it wants. So that's always a fun example.
I wouldn't call that fascinating. Wow.
And someone's asked, what's the parasite called? So this is a fungal spore within a dead beetle. So if you just Google the fungal spore, I think I've got a link. Yeah, here it is. So I've got so it's a goldenrod soldier beetle. That is the beetle. Then it's about this fungus is called, I'll try and find the name later. I can't find it in my notes. But if you Google the goldenrod soldier beetle and take a look at parasite infections, you should be able to find it yourself. But yeah, one of my favorite examples.
Yeah.
So yeah, I sort of mentioned this as I went along. Where's the similarities here in terms of software and biology and the motivations of why bad actors are trying to get in? And they're very similar when you take a look at them. So as Steve mentioned, we might have people coming into our software to steal our data. Well, data is just a form of resource. It's a resource that can be valuable, that can be worth something. And that's the same thing in biology. Bacteria or viruses can come in and try and steal our resources, whether that's food, for example, like energy, or whether that's the resources within our cells in terms of our replicating mechanisms. They'll come in, and again, they're just trying to steal our resources. Another one is changing data. And actually, the same can happen in biology, where what can happen is viruses can actually insert parts of their DNA into our DNA. So when our cells replicate, it replicates the bacteria or the virus as well. And so they can actually edit our DNA, so changing our own data, because our DNA is our data. How about crashing systems? Well, we just saw a really clear example of where that beetle had completely crashed and that parasite had completely taken over. So that's a common example in biology as well, completely taking over control of either an organ or the whole body itself. Stealing our energy reserves, kind of similar to resources. It might be specific here that they're stealing energy, just like that compute power, and very commonly going through us to access others and repeating and repeating and repeating. And that's how the pandemic and things like that can happen so quickly and rapidly, because they can spread so easily, and that's sort of their purpose. So you can see here a lot of similarities between humans and biological bad actors, and also the bad actors that occur in software and their motivations.
Cool.
So
okay.
On to the battle. I'm ready.
Yeah, so remember, we're going to do a bunch of rounds. There aren't that many of them. And this is prevention, which is about the how do you prevent yourself being compromised or infected in the first place? So Grace, all yours.
Bring it on. Okay, biology. How do we prevent? So we have a fantastic range of different prevention mechanisms in our own bodies that help to prevent anything from getting in. The first stage of that is your skin. So your skin is a fantastic organ that allows us to really prevent the number of orifices or openings that allow things to get inside our body. In fact, that's the reason it's so sort of secure in that sense of making sure that if we have, say, a cut in our skin, we immediately repair that and prevent things from getting in. So really, it's a fantastic prevention to be able to stop things from being able to get in any which way they want. We do have to have orifices, though. We do have to have openings. Otherwise, we'd really struggle to get food in and out. So we do have orifices, but at those openings, we have additional defenses. So things like in our mouth, we have saliva, in our nose, we have mucus, in our eyes, we've got tears. So being able to have these extra defenses allows us to add in that extra layer of prevention, even when we do have openings. We've also got additional things like, for example, our behavior. So the fact that we've been able to have sort of enhanced sensors. So for example, if I go to a carton of milk that's gone off a bit, I probably shouldn't drink it because it's not going to be good for me, and I can smell it. Having that enhanced sense of smell, I can taste that it's wrong, it doesn't taste right. Being able to have these enhanced senses allows us to prevent us from eating or drinking or swallowing anything that might potentially provide a route of infection. And behavioral changes in terms of how we prepare food, for example, washing my hands when I've touched chicken or something like that, cooking food, which again helps to get rid of that bacteria, potential food poisoning, etc. So those behavioral changes as well. But this goes not just on that sort of macro level, this goes all the way down to the micro level of cell identification. We have different proteins on the outside of our cells that allow us to identify our cells as ours and other cells as other people's. So when there's an external cell, whether that's a virus or bacteria or whatever, trying to get in, it can recognize that as, you don't belong, you shouldn't be here, that's not me. And then it can act on that and again, prevent anything from being able to disguise itself and sort of sneak into your system, sneak into your body. So we've got loads of different ways to be able to prevent that initial sort of infection from various different bad actors. What about software?
Well, we have some of that. There's no doubt that. I would like to point out, because I just love doing this talk with you, Grace, is that this is the only software talk where we get to talk about orifices. It's just, it's the schoolboy in me, but there we go. So we've got things like API gateways. They are mechanisms for ensuring that there's only one route in. So we talked about the O word. We have API gateways. If we use API gateways, then we have that protection because there is software out there that's designed to look at the traffic coming in and trying to understand whether it's good or bad and reject it. So we have defenses like that if we use them. Now, there's something that developers can do. As developers, we can't just rely on API gateways. We can't ever just rely on everybody else fixing the problem. So as developers, what we should be doing is putting effort into our prevention, and that's how we write code in the first place. So there's lots of things about how you write code, but the obvious things are, do we have the right authentication model? Have we designed that correctly? And what are we doing in terms of checking that the data that comes in is valid? And not just, is it within a valid date range, but also like the combinations of data and do they make sense? So we can prevent these things if we put effort into applying the right sorts of checks and balances within the code. Now, the other things that we have that help prevention, so the obvious thing is dependency management tools. So we all know about things like Log4Shell and others where it turns out that we had some vulnerability in our class path and it gets exploited. So the longer it takes you to fix that, the more open you are to being attacked. So one of the most important modern tools in terms of prevention is to manage your dependencies and to keep up to date all the time. And we'll compare that with like being vaccinated, because it is very much like that. There's a nasty thing out in the world. How do you prevent yourself being infected? Well, one of the obvious things is that you keep your dependencies up to date, and you do that as quickly and as seamlessly as possible, which brings on to the high-speed thing. What we have to point out nowadays is that the time that you have between one of these nasties turning up and it attacking your system. So, Log4Shell is a really good example. We're all aware of it, and we're all aware of how much effort was put into by the industry to fix it. That was announced after the fact. So it had been discovered by the bad actors it was being used. It got reported. So we had no time. It wasn't a situation where we knew this was going to happen. It was already happening. So nowadays you can't wait. So you have to have these high-speed systems. If you have good build systems, good CI/CD systems, you can just press a button, update the dependency, do the test, and done. Then that's a big prevention mechanism. So basically, if you've got these things, you've got good dependency management, you've got a good CI/CD system that's automatic, that drives fast. You have API gateways to stop the bad guys coming in, and you have the security checks and input validation as the backstop, then I think we're doing pretty good. I'm quite happy with that one.
Yeah, I
What do you
think,
think, Grace?
given all of that, I reckon it's a draw for this
Way!
round.
It's always, yeah.
Yeah, I think looking at the summary, as you say, there's a lot of the defenses that we have in software that people, it might be the case you might not be using all of them, but they're out there, they're available, and they match some of the sort of defenses that we have within biology.
Yeah, and I like the washing hands analogy, and I think that as developers, that's one of the things that everybody should take away is okay, it may be hard to get your head around this about what you can do, but it is the time to start, and it's the time to work out what washing hands means for you, and in your circumstance, what is the everyday activities that you do that just keep things just a little bit safer. Yep.
All right, okay. Draw for round one.
Draw for round one. I feel confident.
Bring on round two, detection. Yeah. Okay, so this is where we're going to take a look at, okay, now that you've been infected, unfortunately, the prevention doesn't always work in software and in biology. You know, we still get colds, we still get flu. So what happens when we are infected? How do we detect that we've been infected with something? So taking a look at biology, well, I'm sorry to say, Steve, but we've had billions of years of tuning. So
we're intelligent human beings.
I'm going to see the difference here. Yeah. So we've got various different ways of detecting when we're infected. So we have the innate immune system, which can include things like the skin and just the mucus and things. That's the things that are already there to prevent stuff from getting in. So it's stuff that's just innately there. But we also have the adaptive immune system, which is where we have things like our white blood cells and being able to have antibodies that can detect infection. So having white blood cells, having antibodies, all of these allow us to rapidly recognize and identify and do stuff about infections when we find them in the body. And that's kind of the point of vaccines is when we have a vaccine like the COVID-19 vaccine, for example, we're essentially infecting our bodies with either a dead or a sort of replica version of that virus or that bacteria or whatever. And it means that our bodies can then start to recognize it. So we can start to have more antibodies, more white blood cells within our system that have already recognized it once before, so should be much quicker at detecting it in the future. We also have this rapid learning, which is sort of where that vaccine comes in. Being able to rapidly learn as we get infected with more sophisticated bad actors, as they evolve and as they change, being able to learn from this and adapt our own responses to that. Extra protection through the use of vaccines, so stuff that perhaps our bodies wouldn't naturally get, but that we can do ourselves to be able to help our bodies to be better at detecting and be better at responding. We've also got, all the way down to sort of the cell level, we've got this self-destruct ability, which is really cool, where essentially if a cell within our body recognizes that it's been infected, it will signal to our immune system to say, hey, like I've been infected, kill me so I don't infect anyone else. So it's this fantastic sort of self-destruction capability that is for the greater good of the body to prevent the rest of the cells from being infected before it can spread beyond that single cell. Other detection that we have is more sort of abstract. So things like pain or even deferred pain. So a lot of the time, pain is usually the result of being able to sense it and have sort of our nervous system will respond to that, connection to our brain, and our brain will say, oh, I've touched a hot pan, that hurts. That kind of pain helps us to know, when we are doing things that perhaps are bad for our body, but we can also have things like deferred pain, where internally we might not have nerves that connect to those organs or connect to that part of the body. So we might have deferred pain where that pain is transferred to a different part of the body, so we can still detect that something is wrong, but we might not necessarily know exactly where it is. A common example of pain as a detection signal is a headache. And what we often do is, instead of saying, why do I have this headache? I'm probably dehydrated, I should drink some more water. Instead, we take the easy solution and we go, painkillers, that will solve my problem. And often what we do is we hide these detection signals instead of actually getting to the root cause and trying to find out, what's caused this pain in the first place. What can I do to actually get to the root cause and fix that? And so that's sort of another way of detecting when things might be wrong in the body and we need to do something about it. And how sometimes our behavior can almost mitigate that and stop our bodies from doing this fantastic process that we all sort of need. So that's biology. Bring on software.
Okay. So the obvious thing is we don't really have pain, and I think that is, so can we fix that? Don't know. But if we look at what we do have, it's not the greatest. We're just not geared up to deal with this idea that something bad is going on without the specific tools. And there are two types of tools that we can talk about. There are tools at the front end, like the API gateways, where there are tools that can monitor unusual patterns. But that's, once you get past that, once they get into your system, it's like, what is it that you could tell you that things are going bad? Where's the pain? And well, as you can see from this screen, like system crashes, that's a common one. But even that is, the first time that happens, you go, oh, the system crashed, and you go, oh, what did I do? Did I not give it enough memory or something? And we just assume that it's not a bad actor, it's just coming in because we did something wrong. But it would be the first indicator that something's wrong. So it's sort of like your system died. Not the greatest way to detect this is happening. You might get, and in fact, we all get things where we get some complaints from our users who tell us things like, oh, the system's got a bit slow and it's not behaving as well as it should do. So we get that, cool, okay. We probably don't know how to separate that from cause as to whether it's something that we did or whether it's a bad actor, because we're just going to measure it at this very gross, oh, it's got a bit slow. Ransomware will spot. Ransomware is intended to be spotted. Ransomware is where you come in one day and you can't access your system, or you can actually pass some part of it, but somewhere there will be a big notice that says you have to pay money to get your data back. So that's deliberately intended to be detected. So maybe that shouldn't even be on this list, but it's a way of knowing that you've been compromised. And then the last one on this list, which is, again, just horribly scary, is that you can find that somebody who, and there are lots of companies out there who are scanning the dark web, government agencies and commercial entities who are looking to find the data, because obviously if we can figure out that some of your data has been leaked onto the dark web, then we can come around and talk to you and say, hey, you've been compromised. But it's not the best way to discover that you've been detected for sure. Can you hear the next one, please, Grace? Thank you. Yeah. So there are tools out there. There are monitoring software tools, there are performance profiling tools, there are AI tools turning up that are being trained to spot these attacks and to figure out that maybe your logging has got error messages in it that were unusual, and there are patterns that are coming through there. There are AI tools that will look at your performance profiles and look for spikes and things like that. But you have to have these tools in place. You don't get this as developers. We don't get this for free. Somebody has to do this. And it's, as it says, it's indirect, because most of the time when this goes wrong, we find out after the fact, and we're pretty much like the beetle, our systems have been broken. We could do things about it. And one of the things that we could do as developers is go look at these tools and understand how they behave and understand our responsibilities in terms of working with them, and maybe looking like putting out more information so that these tools have got more data to hook on. And that's our pain sensors, where we look at the behavior of our application, not just errors. Start thinking about how you might spot just unusual things. Look at the code flows that you've got and figure out whether there are code flows that don't happen very often and should be flagged when they do, or just unexpected. And the more that you can instrument your system so that these tools can hook in, then the more chance we are of spotting that these attacks are taking place. So there we go. Do we win, Grace, or?
I'm going to say biology wins on that one.
Yeah, I think so. I think it's mostly because us human beings need to, put a bit more brain into it.
That and the fact that, when a software system crashes, yes, it's bad for enterprises. Yes, it's bad for the business. But at the end of the day, you spin up a new container or you spin up a new pod and you've got your application back. That the same can't be said for human beings. Once we crash, that's kind of usually the end of it. So although biology does win here, we have had the advantage of billions of years to perfect this, or at least get it to a very effective level. And if we didn't, we wouldn't be alive and healthy, and we wouldn't be here today.
That's very true. So it would be, I think it would be the wrong approach to tell developers that if their system crashes, then we may terminate them themselves. So I think that's not the way to go. But I do get that we really need to look much better at this and think much harder about how we can, as developers, we can help detect these situations. And I know it's hard, but we've not really looked at it before. So there's a load of opportunity for people who want to think differently and go out there and see if they can solve it.
I think the quote at the end of this slide is one of my favorites. A dull ache is better than nothing.
Better than nothing, yes.
Make
exactly.
your dull aches and listen to them, please. Yes. As annoying as they might be.
Yes, make your application ache.
Yep.
Yeah.
Cool. Okay, round 3, the last round. So we've been infected. Now, how do we deal with this infection once it's in? Can we mitigate the impact that it's going to have on our applications and on our bodies? And how do we go about doing that? So I'm going to go first again. Biology. Yes. Okay, so again, we have an advantage here because this is essentially life-threatening, potentially. So we do have to take this seriously in biology. And if we didn't, we wouldn't be here today as human beings. And so we have really gotten a really effective system going in terms of actually mitigating the impact of potential infections and limiting their spread through the body, limiting their impact. So first things first is going back to the idea of vaccines. So it's not just sort of what biology and nature has enabled us to do, but also what we've managed as human beings in terms of pushing forward our medicine and scientific research and allowing us to have this additional sort of mitigation factor where through the use of vaccines, we already have white blood cells and antibodies ready to go in our system that can prevent or at least attack when we have those potential infections. The other thing is that adaptive immune system, being able to adaptively learn as we get new infections. So, for example, a great example is the various different strains of COVID-19. So we've all heard of the various different strains, and they are each themselves slightly different in terms of how they present themselves. And so even though we might have a vaccine for one particular strain, that will then help us in terms of learning from that if we do get infected with a different strain of that same type of virus, for example. Another thing our body can do is make itself less habitable. Naturally, our bodies are actually a really lovely, cushy place for infections to come and live. And so what our bodies try and do is make it really uncomfortable when we do get infected. What that means for us is we're also uncomfortable. So although it's a pain when you get, when you're shivering, you've got a fever because you might be infected with something like the flu, for example. Yes, it's uncomfortable for you, but deliberately so, because it's also uncomfortable for whatever's infected you. So our body does things like raise our temperature, for example, and all of these kind of different sorts of changes to make our body less habitable and less cushy to live in. Another thing it does is, a really important thing is getting rid of those foreign cells, getting rid of those infections. And I'm hoping it's not too close for lunch for everyone, but either going up or out, either way, Getting rid of those infections. So for example, when you have food poisoning, that's a classic example where we rapidly try and empty the contents inside us to prevent that infection from getting any further and from spreading, and just to get it out the body, basically. Another thing is coating our DNA. So I mentioned that some viruses, for example, can actually insert their DNA into our DNA. To prevent that, our bodies have actually evolved this ability to create molecules that can suppress viral genes from being able to be inserted or from being replicated when we replicate our cells. And other things, which we've kind of already touched on before, but really limiting access through the body. And where we do have access, making sure that we're patrolling those routes with things like our white blood cells and our antibodies to ensure that if it does get in and it is traveling around the body, we can shut it down as soon as we see it. And really essentially have bodyguards monitoring all of the routes within our system. So we have loads of different, right down from the cell level to the behavioral level, we have lots of different ways of mitigating the impacts even when we are infected with a potential infection. What about software, Steve?
Well, okay. I'm sure we can outdo biology. So I suppose the first thing to say is that mitigation right now is limited to things we do up front. There is a little bit of what you'd call active migration available, but mostly it's about what we're doing within the systems, how we think about them, so that when damage occurs, it's mitigated. So the most obvious one, and I'm not even going to touch this other than to point it out to people, is that amazingly, there are a whole bunch of really good principles for designing your systems, and there's a few of them, but you can go to the OWASP and you can go read these things, and there is all sorts of information, loads about that. I mean, software security design principles have been around for a very long time. There's lots of good advice, and it's really about, well, go read this stuff. Go have a look at it and translate it into your programming language and your frameworks and your situation, because there's nothing in here that is anything other than really good, solid advice. So that's the first thing. Yeah. Now, having said that, we actually quite often do exactly the opposite, and we don't actually follow secure design principles because we're not aware of them. And in fact, we tend to do them quite often in reverse, and we tend to just do the opposite. And one of them is code quality, because amazingly, what the bad guys are going to do is drive your code, or try and drive your code in unusual ways. So they will go through all the if-else paths through your system. I mean, they may not have access to your source code, but they can drive the data and get different results. And so what they're looking for are all those strange paths through your code that the code set is valid, but actually you never expected to have happen. Because that can get them to places that to break out of your authentication processes, or just get at things, make your system crash, you name it, and they're doing it through your code because your code is not very good from a quality point of view. So one of the most effective ways that you can do once you start looking at design principles is to improve the quality of your code and make it understandable and readable. Yeah. And then data. So how do you think about this? How do you start looking at what you give out? So here's a really good example of how you should think differently, because this is, it's a fake example, but the way to read this is to think about how you create APIs. And as developers, we're very good at cutting corners, whether it's because we don't understand the consequences or because we're being pushed. So we have two examples. We have on the left, we have users, and on the right, we have user delivery. Quite often, when asked to provide, say, an address to an application. So imagine I want to get the address of somebody because I want to print a label. So in the as a developer, you might go, well, that data is okay. The data is in the user record, so I'll just give the label program the user record, and they can just use the bits they want. However, that means that you expose more information, account numbers, emails, names, and things like that. And that is a bad idea, because you're conflating use cases. And when you do that, if one of those use cases gets compromised, then they all get compromised. So the better way to think about it is to start looking at how the data you bring out is the least you have to do to allow that use case to happen. And on the other side, the user delivery, you can see it's just the information you need to get the address. Okay, thank you. Next one, thank you. Yeah. And the other way is to mitigate is not only just by breaking down its use cases that reduce the data being given out, the way that you present the data should also change. Now, there are two pieces on here. They're a bit complicated, but basically the first one at the top, the calendar API, returns some schedule. You can imagine you want to get a list of dates from the system because you want to put them up, and that's fine. However, dates are recognizable, and lots of the probing systems that bad guys use to get into your system will be driven by bots. And one of the things they're looking for is recognizable information. And if they can find recognizable information, they can reuse it, and they can possibly get human beings involved. So the way to start reducing that possibility is by thinking differently. So the second one below looks at a different way of giving back exactly the same information, but rather than giving out raw dates, it goes offsets. Because now the bot's got to figure that out. Maybe offset's the wrong word in this data, but you get the point. It's don't give out raw data, find ways to make it still useful. But you've got an API, so you've got a date, you've got a program at the other end. So you've got another programmer who can be told what format of data is and can code it accordingly. But you reduce the chance of the bad guys compromising your APIs. And that goes the same as we're saying here is think also about authorization, authentication, everything around use cases, not superpowers. We're very good at having a thought process along sort of an onion model where you have no powers all the way through to superpowers or root. And we think each one is a progressive gaining of powers, and it shouldn't be like that. Each time that you do that, and therefore once one of those levels gets compromised, they gain everything. Much better to look at using it for use cases, and you authenticate and authorize by particular use cases. That way, if somebody gets into the calendar system, they can't find the addresses and vice versa. And that's how you really have to think about that. Okay, thank you. So yeah, mitigation. Having been probed, having been attacked, having the bad guys getting into your system, we just don't report anything. And so now you have to start thinking about how can I tell that I am being compromised? And it says here microservices may be stateless, but the data is not. Maybe one of the things you can start thinking about recording is the activities that the data is going through. It represents the state of some applications, some user accounts. Keep track of how things are applied to it, because maybe you can spot that there's some trend going that you weren't expecting, right? And every time that you can see something that's unusual, you log it. Not necessarily an error, just a log it. Yeah. Sorry, can you go back one, Chris? Sorry. Just yeah. Because there's one more thing. Don't think that these botnets, that it's one person out there, it's a botnet. Think about what happens when these attacks are spread across hundreds, millions of IP addresses, right? So you can't guarantee that you can spot that there's a bad individual, but you can spot if your data is being manipulated in unexpected ways. Okay, thank you. Next one. Yeah, so handle errors. Hey, we're good at this one, aren't we? How many people have written something like the red on the left, where you go, I know what errors you're going to get, and I don't care about any of them, so I'm just going to capture them. And the problem with that is that your assumptions are always wrong, because when errors get thrown, you should look at them and say, okay, this file error turned up. Why? And if you weren't expecting it, then log it. Don't swallow it. And if you can separate out the errors, like on the left, on the right, where you've got file not found versus IO exception, do so, because it will help the tools that are looking at your logs to spot that unusual behavior is happening. So that's really critical part of this. Okay, and now this one might not occur to you, but test your dependencies. So what that means is that you can't rely on the dependencies to do the job, because as the black thing on the right there, recently we saw a spate of people doing what's basically called protestware, where a dependency that had been used for ages suddenly was corrupted by the author of the dependency because they were protesting, but it could have been by a bad guy. So if you don't test your dependencies to make sure that the features that you rely on continue to work, you may not realize that you've been compromised. So you don't have to write loads of features, loads of tests, but at least start thinking about how you prove that it does what you expect. So when it does change, then you catch it. Cool, thank you. Oh yes, how long before exploitation? How long between the bad guys finding out that a vulnerability exists and them probing your system? So this is a chart that's been around for a long time, as you can see, and way back in the heady days of 2006, the time between a vulnerability being discovered and it being made available was 45 days. Sway, you roll forward to today, log4j. Well, next slide, please. It's closed. Log4j came out. We've heard about Log4j after it being exploited by many bad guys. So you have no time. You just have to deal with the fact that any vulnerability you hear about may already have been in the wild for some number of days, and you have to treat it with that level of urgency, whatever its level of severity. Cool, thank you, Grace. Next one.
Okay, so I'm gonna call biology a winner again.
But why? Yeah, okay.
So
yeah.
Again, I've got the advantage here in terms of, there are serious consequences if we fail within biology. There are no reboots, and it's critical that we're always aware of this changing environment. Don't get me wrong, the consequences in software are growing. They're getting higher. As you say, we've got less time to deal with stuff. The consequences can be more severe, but at the moment, our mitigation strategies aren't necessarily at the same pace as biology. But I think they're getting there, and I think there's more that we can do as developers to ensure that mitigation, like you say, good code quality, dependency tests, etc.
So does that mean I win? Do we win this time?
I'm afraid Mother Nature wins again. After 3 rounds, I won 2, we drew 1, makes me the winner. So although Mother Nature did win, hopefully what we've shown you through this presentation is these key takeaways. That, living organisms have this amazing robustness to be able to adapt and deal with various different external threats, and that Java applications have many of the same abilities through things like tooling, testing, development processes and methodologies. And that's what we need to be thinking about throughout our development lifecycle, is really how do we design for defense and defense in depth. So all the way through, not just right at the start when we're starting to develop, all the way through to in production. So really take the time and understand what security measures you have in place and whether you could improve those through some of the things that we've mentioned in this presentation today. Your application is in this ecosystem of the cloud. You are one application. Make your one application or your one cell a very effective one, especially when it comes to security.
Yes, thank you.
We have some useful links for you in case you want to go deeper into this subject. We've got some interactive guides. We've also got some documentation. We've got all the resources over at Sonatype that you can take a look at, and those security design principles that Steve mentioned from OWASP at the bottom there. So with that, we're pretty much at time. Thank you so much for having us. It's been a pleasure to be here. If you do have any questions, we can take a look at them in the chat and answer them, or you can connect with us on Twitter. Our handles are there.
Exactly, yes. Thank you, everybody, for watching. Thank you, Grace.
Thanks very much.